Okay, so you know this pattern we've talked about so far, that the degree of the polynomial is how many zeros it should have? Well, that actually has a name. That is called our fundamental theorem of algebra. And the fundamental theorem of algebra just says whatever the degree is, that's how many zeros it should have. So we're going to experiment with that a little bit with a couple examples. I start right here. So this is a degree 1. That's the biggest exponent it's got here, is degree 1. So if we look at the zeros, remember to find the zeros, you set the equation equal to 0, which usually means you have to factor it. But because this is just a linear, it's already factored. So our zeros are x equals 2, and that one has a multiplicity of 1. Ta-da! So degree 1, and it has one answer. So our fully factored form is just x minus 2. So let's try a slightly harder problem. X squared minus 4x plus 4. Well, we can factor this. What multiplies to 4 and adds to negative 4? That'd be negative 2 and negative 2. So this is x minus 2 squared. So this is a degree 2. That's my biggest exponent. If I set my factor equal to 0 and solve, I get 1x-intercept at 2. But this x-intercept has a multiplicity of 2, because that's the exponent on the factor. So degree 2 still has 2 zeros. 1x-intercept, but it has a multiplicity of 2, so that makes it 2 zeros. So if I wrote my factored form, it would be x minus 2 squared. So far, so good. Degree 2, 2 answers. Let's move to a slightly harder one. This one. This one is degree 3, so we should have 3 answers here. So let's factor and see what we can get. I notice that they have a 3x in common, so that gives me an x squared plus 4 left. I set these equal to 0 to find my zeros. And I have 3x equals 0 and x squared plus 4 equals 0. So there's one of my answers, has a multiplicity of 1 because that's the exponent on it. If I go to solve this one, I get that x equals plus or minus the square root of negative 4. Which we just learned is actually plus or minus square root of 4i, and square root of 4 is actually 2. So this is plus or minus 2i. So I have a 0 at 2i and a 0 at negative 2i. Both of them happening once. So degree 3, I have 1, 2, 3 answers. So my fully factored form would be this 3x, and this x plus 4 will actually factor more. That x squared plus 4 became our 2i and our negative 2i. So if this is in 0 form, in factor form, that would turn into x minus 2i. We'd minus 2i to both sides to get it to equal 0, and x plus 2i. And that's my fully factored form. So if you remember in 2.4 last lesson, we were talking about difference of squares. And we talked about how if it's a plus instead of a difference, we can still factor that, but it's with imaginary numbers. Well, here's how we do that. Difference of squares, so if this was x squared minus 4, would factor as x minus 2x plus 2. Square root of 4 is 2. The addition of squares, x squared plus 4, would factor as x minus 2i, x plus 2i. Those are the two different versions we've got. If it's plus, it's imaginary. If it's minus, it's just difference of squares. So, point we were trying to make though, degree 3, still have 3 answers. So far, so good. Let's move on to our last one. X to the 4th minus 16. We can factor this. Oh, sorry, before I factor, this is degree 4, so I should have 4 answers. This is difference of squares. X squared minus 4, x squared plus 4. Take the square root of x to the fourth gets me x squared. Square root of 16 gives me my 4, plus or minus. And this is difference of squares. X minus 2x plus 2. And this is our sum of squares. So that's our imaginary one. So this is my fully factored form. And if I take each factor and set it equal to 0, that will give me my 4 zeros. So I have a 0, x equals 2, x equals negative 2, x equals 2i, x equals negative 2i. And they all have a multiplicity of 1. So degree 4, 4 answers, it still works. That is why it's called the fundamental theorem of algebra. Whatever the degree is, that is how many answers you should get. Now, one thing that you may have noticed about my imaginary answers. The imaginary answers always come in pairs. The plus or minus 2i, plus or minus 2i. And that is actually something that will always be true. This is our conjugate pairs theorem. If a polynomial has a plus bi is one of the zeros, then its conjugate, a minus bi, is also a 0. Imaginary zeros will always come in conjugate pairs. So that's why I had positive 2i and negative 2i as a conjugate pair. And that will always hold true. Always. If you will never just have one imaginary zero. They always come in conjugate pairs. So, knowing all that we've learned about imaginary numbers, in the next video, we're going to use all of that, everything we've learned this chapter, 2.2 through 2.5, to fully factor this x to the 5th. So we're going to use our rational zeros theorem and list our possibilities. We're going to do synthetic division. We're going to factor everything out. We're going to use quadratic formula and imaginary numbers. We're going to do all of that stuff, put it all together to fully factor this polynomial.